Chapter 11, Equilibrium and Elasticity. It covers equilibrium conditions, the center of gravity, elasticity. You can find them in the timeline. Equilibrium conditions. Equilibrium. Consider these objects. 1. A book resting on a table. 2. A hockey puck sliding across a frictionless surface with a constant velocity. 3. The rotating blades of a sailing fan. And 4. The wheel of a bicycle that is traveling along a straight path at constant speed. For each of these four objects, 1. The linear momentum p of its center of mass is constant. 2. Its angular momentum L about its center of mass or about any other point is also constant. We say that such objects are in equilibrium. The two requirements for equilibrium are then P is a constant and L is a constant. We are concerning largely with objects that are not moving in any way, either in transition or in rotation, in the reference frames from which we observe them. Such objects are in static equilibrium. Of the four objects mentioned at the beginning of this section, only one, the book resting on the table, is in static equilibrium. That is, its linear momentum p equals 0. If a body returns to a state of a static equilibrium after having been replaced from it by a force, the body is said to be in stable static equilibrium. Now, like this one. You move a little bit, it will come back. Okay. A marble placed at the bottom of a hemispherical bowl is the example. If, however, a small force can displace the body and end equilibrium, the body is unstable static equilibrium, like this one. You move more, it will falling down.
We'll use these objects to demonstrate three different types of equilibrium. This cube is in stable equilibrium. If it is displaced by a small amount, it returns to its original orientation. This sphere is in neutral equilibrium. It is stable in its original orientation and in any other orientation. This cone is in unstable equilibrium. If it is displaced by even a small amount, it falls over, instead of returning to its original orientation. This animation shows the weight that acts on the center of mass of each of the objects as it is tipped. This chair can be mounted on a sharp point at the top of this bar. The chair is now stable in all orientations and can be swung vigorously without tipping from support. Why is the chair so stable? Weights have been added inside the legs, which lowers the center of mass to below the point of support.
This toy clown is stable when placed on a tight string. Why doesn't the clown fall off the string? These weights shift the clown's center of mass to a point below the wheel. If we remove the weights, We shift the center of mass to a point above the wheel. Here's what happens without the weights. With its center of mass above the wheel, the clown is no longer stable.
There are many situations for equilibrium in the nature, Pisa Tower, and so on. The analysis of static equilibrium is very important in engineering practice. The design engineer must isolate and identify all the external forces and the torques that may act on a structure, and by good design and wise choice of materials, make sure that the structure will tolerate these loads. The requirements of equilibrium. 1. The vector sum of all the external force that acts on the body must be 0. Now, sigma F external equal to 0. That means, the linear momentum P equal to constant, because the change rate of linear momentum equal to sigma F. 2. The vector sum of all the external torque that acts on the body measured about any possible point must also be 0. Now, sigma torque about any point equal to 0. That means the angular linear momentum L equal to 0, constant to equal to constant. These are necessary but not sufficient conditions. You satisfy this question, this might not be equilibrium. The linear momentum P of the body must be 0. Now, you want to make it sufficient, the P must be 0. In other words, the velocity should be 0. Balance of forces. If sigma F equals to 0, sigma Fy equals to 0, sigma Cf, balance of torque. Sigma tau x equal to 0, sigma tau y equal to 0, sigma tau z equal to 0. Under this condition, there be chance be in equilibrium. If this is a two-dimensional, then we get fx equal to 0, sigma fy equal to 0, sigma tau z equal to 0.
This meter stick is free to rotate on a pivot point at its center. Pegs at 3 different distances from the center can hold masses of either 100, 150, or 300 grams. If we put a 300-gram mass on this first peg, the stick becomes unbalanced. We can rebalance the stick by placing another 300-gram mass on the corresponding peg on the other side. To balance the stick, where should we put a 150-gram mass? We put it twice as far from the center as the 300-gram mass. Now we remove the 150-gram mass. Where should we place a 100-gram mass to balance the stick? We put it 3 times as far from the center as the 300-gram mass. Here's an interesting puzzle. If a person balances a meter stick on 2 fingers, with one finger closer to the end of the stick than the other, and then slides both fingers in towards the center, which side will the meter stick fall towards if it becomes unbalanced? The meter stick stays balanced the entire time, and both fingers end up exactly at the middle. Let's watch that again with one of the fingers starting even closer to the center. again, the stick stays balanced. But if we try to reverse the process, the stick falls off. If we cover one finger with a rubber glove and coat the other with slippery chalk dust, will the meter stick give up this time and become unbalanced? Even with such a large difference in friction, the stick stays balanced. If a weight is added to one end of the meter stick and the demonstration is repeated, the stick still remains balanced, but the fingers meet at a different spot.
The center of gravity. The weight W of an extended body is the vector sum of the gravitational force acting on the individual elements, the atoms of the body. Instead of considering all those individual elements, we can say that a single force W effectively acts at a single point called the center of gravity of the body. By effectively, we mean that if the forces on the individual elements were somehow turned off and the force W at the center of gravity turns on, the net force and the net torque about any point acting on the body would not change. Look at this. This is the 1 point. Around this O, we have a torque I equal to distance xi and fgi. This is some point, okay? And then we see the total net charge is sigma tau I, sigma xi fgi, okay? Body as a whole, this is body as a whole. You have a tau equal to x com, this is x com, and fg. This fg is sigma f, okay? This is a net torque. They are the same. We look at it in different point of view, okay? So they should be the same. That x com sigma fgi equal to sigma xi fi. And this one, we know that fgi is mig. This is mig. If all the g are the same, gi are the same, okay? And then we can cancel out this one. What we got? We got x com equal to sigma m and sigma xim. What is this? Actually, this is the definition of center of mass. Okay? This is the definition of center of mass. They overlap. The condition is OG is constant. If G is the same for all elements of the body, then the body's center of gravity is coincident with the body's center of mass. In Fig A, a ladder of length L, 12 meters, and mass M, 45 kilograms, leans against a slick, flickless wall. Its upper end is at height h 9.3 meters above the pavement on which the low end rests. The pavement is not frictionless. Okay, they have a friction. Okay. The ladder's center mass is L/3 from the lower end. It's not uniform. Okay. A firefighter of mass M, 72 kilograms, climbs the ladder until her center of the mass is half L from the lower end. What then are the magnitude of the forces on the ladder from the wall and the pavement? We know that this wall on the top is frictionless. What this mean? This means no friction along this vertical direction. So the force acting on the ladder by this up wall is perpendicular to the wall because no friction, no force along the wall, vertical wall. And in the bottom is friction. It has friction. So it has horizontal friction and vertical normal force and so on. So that's the difference. Okay? Now let's see. This A. This A equal to L squared minus H squared square root. Okay? And then we take point O. This is the point O as a reference point. We see what's happening. We have two things. Sigma F equal to 0, sigma tau equal to 0. Right? Let's see sigma tau equal to 0. How many forces are there? Is that 1, 2, 3, 4, 5. Among these 5, these two forces, their torque is 0. So they do have a force, but they don't have a torque around O. That makes things easier. So we get FW, this one. FWH, this is clockwise, so it's a minus number. And this mg, okay, half A. This is a middle, so it's half A. This is this around, so there's a positive. And small mg, okay, the letter is 1/3. This is anti-clockwise, a positive. And these two forces, they have a force, but they don't have R. So this is 2, 0. Okay? So from this one, I can get FW equal to GA half M. It's very easy to find. Okay? Once we know this one, then we know sigma F equal to 0. Okay? Then we see X we have two forces. One is this, one is this. So this one is easily equal to this in magnitude. Okay? So it's 410. Now let's look at this one. The net force on y direction is 0. We know big mg, we know small mg, we can find this one. Okay, this is the 2. Okay? Then we get everything. Sample. In the figure, a rock climber with mass 55 kilograms rests during chimney climb, pressing only with her shoulder and feet against the walls of a fissure of the width. This is the width, 1.0 meter. Her center of mass is a horizontal distance D. This is D, 0.20 meter from the wall against which her shoulder are pressed. This is the one. The coefficient of static friction between her shoes and the wall is, this one is 1.1. And between her shoulder and the wall is 0.70. It's different, okay? To rest, the climb wants to minimize her horizontal push on the wall. What is this push on the wall? Minimize. The minimum occurs when her feet and her shoulders are both on the verge of sliding. That the force, you put it harder than if you stick. What the minimum is, they're just about to sliding down. So in this case, friction is limited. Okay. A. What is the minimum horizontal push on the wall? N. B. For that push, what must be the vertical distance H? This is H between her feet and the shoulder. The feet and this is H. Okay. If C is too stable. See the question A. How many forces accumulate? We see the net force Y equal to 0. How many net force? No. F1, F2, and mg. Okay? And then F1 is mu and F2 is mu. These two forces are the same. Why? Because you look at this balance, along x direction, sigma f equal to 0. These are the two, okay? Also, so in this case, I get a normal force should be mg over mu plus m. You put this together, you get this one, right? Yeah, from here. Next, B. What will be that? We see the minimum torque Z equal to 0. This is the point that we take a reference, okay? So these two cancel out because they don't have a torque, right? Only 1, 2, 3. Then we find C. About the point O, we have F1. This is a clockwise, so it's minus F1W. And this one is anti-clockwise, it's positive, NH. And this one is going down, you see, so it's D, okay, DMG, plus these two 0. So that's very simple. Then we can get it answer, H equal to F1W minus mgd over n, okay? And F1 is mu1n, okay? Then we get to 0.70.
This boom arm is supported by a wire that is attached to a spring scale. The scale shows the tension which is necessary to support the arm. The arm has a mass of about 2.2 kilograms. Now we'll add 2 kilograms to the arm. Here is the new reading on the scale. Now we'll put 4 kilograms on the arm. Here is the new reading. Now we'll move the pulley holding the wire to a new position. Here is the reading on the scale with the arm empty. Here is the reading with 2 kilograms added.
Do the forces supporting the ends of a bridge change as a heavy bus moves along the bridge, or are they always the same? This demonstration uses a model bridge supported by spring scales and a heavy toy truck to find out. When the bridge is empty, both scales supply the same force to support their end of the bridge. If the truck is placed in the middle of the bridge, the scale readings increase, but are still equal. What if the truck is now moved to the right? Will the scale still show the same reading? The force provided by the right scale increases, and the force from the left scale decreases. As we move the truck closer to the end, the difference continues to increase.
Elasticity. Problems in which there are more unknowns than equations are called indeterminate. Okay. We have all had experience with wobbling restaurant table, which we usually level by putting folded paper under one of the legs. If a big enough elephant sat on such a table, however, you may be sure that if the table did not collapse, it would deform, just like the ties of a car. Its legs would all touch the floor. The forces acting upwards on the table legs would all assume definitely and different values as in the figures, and the table would no longer wobble. But how do we find the value of these forces acting on the legs? They cannot be found from the laws of static equilibrium alone. To solve such indeterminate equilibrium problems, we must supplement equilibrium equations with some knowledge of elasticity, the branch of physics and engineering that describes how real bodies deform when forces are applied to them. Elasticity. When a large number of atoms come together to form a metallic solid, such as an iron nail, they settle into equilibrium positions in a three-dimensional lattice, a repetitive arrangement in which each atom has a well-defined equilibrium distance from its nearest neighbors. The atoms are held together by interatomic forces that are represented by spring in the figure. The lattice is remarkably rigid, which is another way of saying that the interatomic springs are extremely stiff. Many ordinary objects, such as metal ladders, tables, and spoons, are perfectly rigid. Of course, some ordinary objects, such as garden hoses or rubber gloves, do not strike us as rigid at all. All real rigid bodies are, to some extent, elastic, which means that we can change their dimensions slightly by pulling, pushing, twisting, or pressing them. Three ways that a solid might change its dimensions when force is acting on it. Tensile stress, shearing stress, hydraulic stress. What the three deformation types have in common is that a stress or deforming force per unit area produces a strain or unit deform. What the three deformation types have in common is that a strain or deformation forces per unit area produces a strain or unit deformation. Stress is tension or compression at force divided by area. Strain is relative length change or relative volume change. The stresses and the strains take different forms in three cases of the figures, but over the range of engineering usefulness, stress and strain are proportional to each other. The constant of a proportionality is called modulus of elasticity. So that is, stress equals modulus multiplied by strain. Stress equals modulus multiplied by strain. What tension and compression, either pulling out or press in, it will have a delta L. Delta L can be more positive or negative. For simple tension or compression, the stress is defined as F over A, the force divided by the area over which it acts. The force is perpendicular to the area, as you can see in the figure 8. The strain or unit deformation is then the dimensionless quantity delta L over L, relative length change. The fractional or sometimes percentage change in the length of the specimen. FOA, this is equal to E multiplied by dl over L. Strain causes strain. This is modular. The modulus for the tensile and compressive stresses is called Young's modulus and is represented in engineering practice by the symbol E. Because the strain is dimensionless, this is no dimension. The modulus has the same dimension as the stress, namely force per unit area.
We'll show how the stretch of a spring varies with the applied force, using this hanging spring and a set of weights. With no weights added, the bottom of the spring is here. Here is the spring extension with 10 newtons of added weight. $20 newtons. $30 newtons. Now we'll add the same set of masses to a different spring, leaving the markings from the first spring on the screen for comparison. 10 newtons. $20 newtons. $30 newtons.
All materials will stretch when pulled hard enough, even the steel wire. We'll hang increasing amounts of weight on the wire to show how the amount of stretch varies with applied force. This mirror is balanced on a small platform attached to the bottom of the wire. If the wire is stretched, the mirror tips and deflects a laser beam, as shown in this animation. The deflection of the laser beam is therefore an indicator of the amount the wire stretches. $20 newtons. $40 newtons. $60 newtons. The amount the wire stretches is directly proportional to the applied force.
Examples. A steel rod of 1 meter long and 1 centimeter in diameter, hence one subcompact cup. It always hooks low here. The stress is more than SY here. Okay. This is S yearly. Okay. And the relative length change is about 0.5%. If you hang two cars, you call it permanent stretched. If it goes that, you never come back. It's permanent stretched. Okay. So if you put 3 cars, then it'll break. That is stress larger than ultimate. Okay, US ultimate. This here is correct. Okay, this is a relative change. Okay, this is the stress. Although the Young's modulus for an object may be almost the same for tension and compression, the object's ultimate stress may well be different for the two types of stress.
All materials will permanently deform or break if they are stretched too far. But the amount they can stretch and still spring back varies tremendously from one material to another. We'll demonstrate that with these 2 springs, one made of brass and the other copper. The brass spring is stretched out to a distance almost 3 times its original length, and it springs back unchanged. Here's what happens when we stretch the copper spring. Even a small amount of stretch is too much for the copper. It springs back a little, but won't return to its original length.
Stress equals modulus times strain. 2. Shearing. Shearing at force on the surface, not perpendicular, on the surface. So it will have a delta X moment. Okay, we call it F over A equal to G delta L. This is delta L over L. Okay, it's called a shearing modulus, G. Okay. Shearing stresses play a critical role in the buckling of the shafts that rotate on the rod and in the bone fractures caused by bending.
This torsion lathe will be used to demonstrate how the amount of twist in a rod is related to the applied torque. A thin copper rod is held between two supports. This end is stationary, while this end is free to rotate and twist the rod. Hanging weights on a metal band wrapped around this disc supplies the torque. The amount the rod twists can be read on this angle scale. Here is the amount the rod twists when 250 grams is hung from the band. Here is the amount of twist with 500 grams hung from the band. We'll now repeat the demonstration using a thicker copper rod. For comparison, we'll leave the last set of markings on the screen as we take new readings. $250 grams. 500 grams. 1,000 grams.
3. Hydraulic stress. We know that stress equals modulus times strain. Okay, and in our case, it's like you put in the liquid in the water, something like that one. The pressure, the stress is pressure. Okay, this is a modulus called a Bach modulus. This is a relative volume change. Yeah. So the stress is P. P is F over A. The strain is relative change of volume. A B is Bach modulus. In general, solid where their rigid atomic lattice are less compressible than liquids, in which the atom or molecules are less tightly coupled to their neighbors. Next lecture, Chapter 12, Gravitation. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.